I am so glad you convinced me that the family car should be the Defender 110. It is so beautiful inside. It's so comfortable, and it just feels indestructible.
Yes, it really is. I've been waiting a long time for the new model to come out. The Defender 110, I'm telling you, it's my favorite car of all times. It's my third one. You know, I have stories of going off-road. The guy managed the group. He was like, what are you doing in this beautiful car? I'm like, I'm going off-road. He's like, are you sure? Because you can use one of ours. And then they look like Mad Max cars. I'm like, no, we're going to do this. And he was shocked.
Wow. Well, it's great because the Defender has been reimagined for 21st century adventure, and its unparalleled off-road ability, as well as its robust interior, are invaluable whether you're headed towards uncharted territory or just a weekend of exploration. The Defender 110 tackles challenging surroundings with absolute confidence. The SUV conveys strength outside and in, featuring peerless technology like an intuitive driver display and an award-winning infotainment system. That's my favorite part, to keep you connected no matter where the journey takes you. Adventure is unique to everyone, and so is the Defender. Choose from the two-door Defender 90, the four-door Defender 110, or the larger Defender 130 with the ability to seat up to 8 passengers. You'll find uncompromising performance in all three. So pack up and go even further with the Defender 110. Learn more at LandRoverUSA.com/Defender.
Sometimes it takes a different approach to help you unlock your true potential. Capella University's game-changing FlexPath format helps you learn at your own pace and fit earning a degree into your life. From before you enroll to after you graduate, you'll be supported by people who are invested in your success so you can pursue your goals knowing that help is available if you need it. Imagine your future differently at capella.edu.
At Staples Business Advantage, nothing can top the smarts and instincts of the thousands of experts on our team. While AI excels at
processing data, automating tasks, and providing insights for better decision-making.
And when they're used together, they're far more powerful than either is alone.
Whoa. I've never felt more alive.
Let Staples Business Advantage use today's latest innovations, plus our team's experience, to make business easier for you.
Sign up today and save 20%.
Staples Business Advantage.
Business is
human.
One of the smartest people in history, author of Losing the Nobel Prize and Think Like a Nobel Prize Winner. And he did almost win the Nobel Prize. Maybe he will one day do it. Professor Brian Keating, physicist extraordinaire. First, we divide this in two because first, I was really curious about black holes, wormholes, and the beginning of the universe. So we talk about that, and he answers some of my questions, which I'm sure some of you might have as well once you hear them. And then we talk about, we have a part two the next day on just the weird things he's seen on college campuses lately with the whole Israel-Hamas stuff. And we talk in general about when is it worth giving up on a goal or a quest or I don't know, a life path. So we talk about that. Brian Keating, here he is.
This isn't your average business podcast, and he's not your average host. This is the James Altucher Show.
You ever go on Quora when occasionally there's a question like, what's it like to have 180 IQ?
Right.
And then someone answers as if, because they think they have 180 IQ, and they're like, I feel very alienated all the time because no one ever understands me. Or it's like, I process all the information around me so much faster than everyone else that it's hard to then communicate what I'm seeing and feeling because I know so much. Like, it's just, there's so much ego when anyone asks that question on Quora or Reddit or whatever.
Yeah, it's like when someone asks you, you're a comedian, like, what makes you so funny? Like, it's guaranteed the response.
No one ever asked me that when I was a comedian.
It's good because there's no way to be funny. There's no way to answer that question and actually, portray yourself as humorous. Because it's like you're just going to be trying like, oh, I got to make a joke. And Yeah, no, to me it's a no-win proposition. But yeah, I mean, people
But-
say I'm smart, and then I say, well, I have to sing the alphabet song to know what comes after R. You know, it's not what you think. It's not all I'm cracked up to be.
What do you think of the original alphabet was?
What do you think?
Like, there was a discussion on some Facebook thread whether or not it was Hebrew, because Aleph, Bet, was it Gimel, Dalet, whatever. I don't even know the Hebrew alphabet.
Stretching
I'm Jewish.
yeah.
Yeah. But it's kind of like matches A, B, C, D.
Oh yeah. No, that's definitely true. No, so Phoenician and Hebrew are pretty similar. If you look at the actual symbols, they're very different from what Hebrew looks like today. And of course, not too many people speak Phoenician. I always think the most suspicious thing ever found was the Rosetta Stone. If you ever look at the Rosetta Stone, it's got like 3 different languages on it. And it's like just the 3 languages you needed to, decipher every single ancient text ever written. It's too perfect. It's too on the nose.
Think it's a fraud?
There's a good book about it. I haven't finished reading it or listening to it, called like The Language of the Gods or something, or the.
Is that like Eric Fromm?
And people make it out. There is a book by him, but that's not it. No, it's like Simon Winchester. I forget who it is, but I haven't listened to it in about over a year. But the thing is, like, it wasn't so simple. Like, everyone thinks, oh, it's just here's a hieroglyphic of a rooster, and it's next to the Greek letter rho, and whatever. But it was like really difficult to decipher it, and it's almost like magical that it ever provided anything useful.
Well, moving on from the Rosetta Stone and my random question about language, there was a Webb Telescope discovery. I'm very glad you're on today, because there was a Webb Telescope discovery recently that has very much disturbed me about the status of the universe. And so here's the discovery.
Yeah,
they found a massive black hole that dates back to 400 million years after the supposed Big Bang happened. And we've talked about this many times. The cosmic radiation is, how did suns even form in time for 400 million years? How did suns even form in time to create a massive black hole?
Yeah, well, there's a couple ways you could get a black hole.
Could the black hole have existed before the Big Bang?
Yeah, there are certainly claims that there are what are called primordial black holes, so a black hole that was present since the beginning of the universe. That's something that people have considered, because it provides a mechanism to explain another thing we don't understand, which is dark matter. So dark matter is this, with substance that we infer exists because of its gravitational influence on the nearby universe and how our galaxy rotates and how other galaxies rotate. And yet we don't see any evidence for any material like it. But black holes are kind of like idyllic candidates for dark matter. They're not giving off any light. In fact, they swallow up all the light. They're massive, so they have tremendous amount of gravitational force. And so they really behave just like you'd like dark matter to behave. And if dark matter exists, it should have existed very early in the universe's history as well. So that's one candidate called primordial black holes, originating at the Big Bang.
Maybe what you're saying is, maybe with the Big Bang, a lot of atoms and matter spun off, but maybe what remained, sort of like when you smash into a car, there's little bits and pieces everywhere, but some big pieces still exist that weren't really smashed up. Maybe that's these primordial black holes.
Well, a black hole in its most idealized form is just an extremely highly curved volume of space-time. So it doesn't.
Why is time in the equation there? Why can't you just say it's very dense, enormously, almost infinite gravity thing? What does time have to do with it?
Well, because you cannot specify a unique position in space without also allocating the time at which it occurs. So in a sense, having the universe, all sorts of events that happen in the universe it's not possible to decouple the effect of some massive object and isolate it only to its effect on spatial dimensions. So you have to include time. So time is sort of essential. And in the past, before Einstein, time was supposedly thought to be independent of space. So you'd plot like a cannonball, moving at some, going up to some height as a function of time. So time was this independent variable, and you plotted the height of it, and then it operated under gravity, and it would accelerate, and its velocity would change, et cetera. But then Einstein came along and said, well, actually, space and time are one unified entity. And, thinking about them separate would be like, well, trying to understand the motion of an object in 3 dimensions, but only describing 2 of them. And so that would lead to, weird kind of project. Like imagine if you're looking at a cannonball and it shoots up and it makes a parabola. So you're looking at it in a profile. But if you look at it from above, it doesn't look like that at all. It just looks like it moves in a straight line. So suppressing a dimension has grave consequences in terms of your ability to understand dynamically what's occurring. So those are sort of the ways that we unify. We talk about space and time together. And also, if you're near a black hole, time does, depend on how close you are to the black hole and how massive the black hole is.
I don't fully understand when people say this. Like, what's the relationship between time and gravity? So supposedly, what I understand is, and I don't understand why, if the bigger the gravity of the object you're standing on, like a planet or a black hole or whatever, the bigger the gravity, the slower time is to the observer. So like if I watched something fall into a black hole, would it take forever? But to that person, it's just going like normal.
Yeah, that's right. So the one of the key aspects of relativity, even absent of gravity, is that time is not absolute the way it is to Newton. So in Newton, you could plot time and it would be the universal function always flowing at the same rate for all observers everywhere. And in general, that's not possible to have a coordinate system where everybody agrees on when an event occurs, and even whether or not certain events are simultaneous with other events. So you light a firework, in your reference frame. If I'm moving with respect to your reference frame, I might see the effect of a firework happening before I see the cause of you lighting the firework. Okay, depending on my velocity relative to you. So you could have things like there are certain examples where you have, like, let's say in your reference frame, you're carrying a golf club, and that golf club, and you're just fitting inside of your car. But if you're moving, and the golf club is exactly as wide as your car, but if you're moving at very high speeds, the golf club gets contracted with respect to the direction that you're moving it in. And it'll actually be smaller than the width of the car. So you could actually have a golf club that's wider than the width of your car and slam the doors on both sides of it and fit it inside, even though it's too big in a frame that's stationary with respect to the car for the golf club to fit. And that's because of what's called length contraction. So that things get smaller and time scales take longer for things that are moving. But you have to add, so there's no way for you to determine your velocity in the universe. There's no absolute center of the universe from which you can determine your velocity. Velocity is relative to observers, and you've had this experience. Probably you're sitting in traffic, and the car next to you starts to move, and it feels like you're moving backwards, but the car next to you is moving forwards. Or on a train, the same kind of behavior can happen. And you can't really say, unless you have some third person, can't really agree that who's actually moving. Is it you moving? Is it the train moving? Of course, the whole Earth is moving with respect to the solar system. The solar system is moving with respect to the galaxy. So taking everything into account, you cannot say for sure what velocity you have. But acceleration can be determined. So you can actually, observers will agree that one entity is accelerating versus another entity. So if you have a rocket moving through space at constant velocity, you can't determine if you're in acceleration, but you can if you're moving with constant velocity. But if you start to accelerate, then you start to experience phenomena that can allow you to determine that you're accelerating. So it's kind of like you can see something, you can determine the properties of something that's more sophisticated. Acceleration is a higher order calculus, function, a derivative, technically it's called. Than is velocity, but it is actually easier and more agreed upon when something is accelerating as opposed to something that's moving at constant velocity. And gravity is indistinguishable from acceleration. So if you're in a rocket and the rocket has no windows and it's accelerating at 1G, you can't tell if and it's accelerating upwards, you can't tell if you're on the Earth's surface stationary inside of an elevator that's not moving, or you're in this rocket accelerating through the universe at 1G. There's no experiment that you can do to tell the difference between those two phenomena. And they're very different, right? Gravity versus motion. And so once you have something moving and accelerating, then you can say that it actually is its time that it experiences will be degraded relative to how it would be behaving if it wasn't being accelerated. So the stronger the gravitational field, the stronger the acceleration, the slower time seems to elapse.
So that's why if someone's falling into a black hole, it could seem to an outside observer like it's taking forever for this person to get to the center of the black hole.
Yeah.
But for that person, he just falls right into the black hole.
Yeah, eventually.
Now, if you're near a black hole for a little bit and you get out of it somehow, is that you're in the future, right? For us, a lot of time has passed. But for that person, no time has passed.
Well, yes, in a sense. So there are two regions of the black hole. One is called the event horizon, things inside the event horizon. Once you go beyond the event horizon, you cannot escape out of the gravitational potential of that object. So it's sort of like if you throw a baseball on the surface of the Earth, if you throw it at less than the so-called escape velocity, it will always come back down to Earth. If you throw it greater than escape velocity, which is like 10 kilometers per second, it's very fast, it will go and leave the Earth's gravity forever. So that's purely the velocity. But the black hole, once you get inside the event horizon, there's no way out. So every possible path that you could take will always take you to the singularity at the center of the black hole. There's no way to escape that.
Small business owners are savvy and know how to get maximum value from their monthly business purchases. The enhanced American Express Business Gold Card is designed to take your business further. It is packed with benefits and features like 4 times membership rewards points that automatically adapt to your top 2 eligible spending categories every month on up to $150,000 in purchases per year. So you earn more where your businesses spend the most. Plus up to $395 in annual statement credits on eligible business purchases at select shipping, food delivery, and retail subscription merchants. So with flexible spending capacity that adapts to your business and access to 24/7 support from a business card specialist, you can continue to run your business with confidence. The Amex Business Gold Card, now smarter and more flexible. It's got the powerful backing of American Express. Enrollment required, terms apply. Learn more at americanexpress.com/businessgoldcard. According to Forbes, January is the hottest month for hiring. I guess all these business owners have their New Year's resolutions and they say to themselves, okay, I'm really going to grow big this year. But the problem is, and this is true for any business owner, your most important asset is the people you hire. It doesn't matter what your idea is. It doesn't matter how big the market is. As an investor, I can tell you, I want to know that you hired great people, and that is really hard to do. So right now, this is why I love this company. You need ZipRecruiter. ZipRecruiter's powerful matching technology finds the right people for your roles fast. And right now, you could try it for free at ZipRecruiter.com/James. Don't forget that /James part. So how are they so good at finding the right people? Well, immediately after you post your job, they use their smart technology that starts showing you candidates whose skills and experiences match the job. And to encourage top candidates to respond to your job post even sooner, ZipRecruiter lets you send them a personal invite to apply. And I've even signed up for ZipRecruiter as a potential employee, and every day I get opportunities to apply for all these like incredible jobs. So I just wanted to see how ZipRecruiter worked, and I can tell you it works. So this month, find the talent you need to fill all of your roles with ZipRecruiter. See for yourself why 4 out of 5 employers who post on ZipRecruiter get a quality candidate within the first day. Just go to this exclusive web address right now to try ZipRecruiter for free. ZipRecruiter.com/James. Again, that's ZipRecruiter.com Quora.com/James. ZipRecruiter, the smartest way to hire. I have a question about this. When we look at a black hole, do we see the event horizon? Do we know where the event horizon exists?
Yeah. Well, so we've actually made images of it. Not me, but there's a telescope called the Event Horizon Telescope. It's actually an array of telescopes all over the Earth's surface, from Chile to the South Pole. And it has taken very high resolution images of the black hole at the center of the Milky Way.
My question then is, if we can see the event horizon, doesn't that imply some energy is leaving the black hole because we can see it? Like,
Yeah.
we don't know something exists unless like light is emanating from it or bouncing off of it. Like something. That's why I see you. That's why I see the chair next to me. It's because something's coming from that object.
Right.
But a black hole, supposedly nothing's coming from it.
Right. So anything that's coming into the black hole will be on a trajectory that will, say, come radially from some distance and eventually fall into the black hole. And there's stuff behind it. So there's an object that just now is entering the black hole's event horizon. And right before it went into the black hole's event horizon, there was light coming from this object. Say it was super hot gas, because things do get accelerated to almost the speed of light as they fall into the black hole's event horizon. And right before they fall in, they're bumping up against each other. They're emitting large amounts of X-rays and visible light and even radio waves. And so the light will come over the top of the black hole. There'll be some trajectory that the black hole from the plane of all the material looks like a giant solar system, basically. That stuff is accreting and spiraling and swirling in to get to the center of the black hole. So there'll be something in the distance behind the black hole from your perspective, and it will have light that'll be coming, just grazing the black hole's event horizon, missing it by 1 millimeter. And as long as it misses it by any amount, it will be bent and then launched on a trajectory, and it'll come towards us. If it's exactly at the event horizon, it will start to orbit around the black hole. So you'll have the light in an orbit. We think of a planet in an orbit, but imagine light being in an orbit, like almost like laser beams going in a circular orbit around the black hole. And then anything closer at an angle that's more steep than that will go into the black hole, and we won't see it. So you're right. We're not seeing stuff that's inside the event horizon. So you actually see a shadow. You see a light shadow where there's no more light that's coming towards you. And then you're seeing a halo around the shadow, the black spot, the black hole's event horizon, of every trajectory of a photon that just barely grazed the event horizon but didn't quite go into it. And these are these images that have been made of these two black holes. One is in a galaxy about 50 million light years away called M87. And then there's one in our center of our galaxy called Sagittarius A star. And that's this giant monster black hole at the center of our galaxy. And so, a friend of mine at Harvard, Shep Doldman, he's been the leader of this project, and they've made images of it for the past, 5 years or so now.
And now there's this black hole from basically the beginning of the universe that, like, black holes are usually made from basically stars that got supermassive and then imploded on themselves and became super dense, hence black holes. But there's this, what you're calling a primordial black hole, which is somehow not that. It's made of something else. We can't possibly know what. And it's right from the beginning of the universe.
Well, it's not quite from the very beginning. So 400 million years after the Big Bang, it's not, it's about 5% of the universe's current age. So it's not time equals zero. So a primordial black hole would be exactly, at the beginning of time. In this case, what they're seeing is a object that they claim in a galaxy, and that the galaxy has an age that they've dated to 400 million years after the Big Bang. So it's not really the beginning of time. In fact, I study something that's 1,000 times older than this, which is the cosmic microwave background radiation. That's 400,000 years old. So there were no galaxies.
Meaning it was made 400,000 years after the Big Bang.
That's
so
right.
Like it's the furthest thing we can really see, because we can't see. It's so dense we can't see past it. past it, we would see evidence of the Big Bang if we could see past it.
That's right. So there's different ways that you could get there. If it was truly primordial, and then it could be primordial and then just be located in an old galaxy, that's possible. But it also could be, and so where would it come from if it was primordial? So there's a theory actually by one of the three recipients of the Nobel Prize, Sir Roger Penrose, your co-author and Think Like a Nobel Prize winner.
That's right.
That
Roger and me.
He conjectured that there are actually black holes are one of the few things that can survive the collapse of a previous universe. So he believes that our universe began thanks in part to the death of a pre-existing universe, as we talked about many years ago, and different scenarios of how the universe could begin. And the question of whether or not that scenario is true. Nevertheless, it's possible that this black hole could have come from the collapse of another universe where these black holes, you really can't destroy a black hole. They only get bigger and bigger as they accrete and accumulate more and more mass, just like we do in middle age.
But if that theory was true, then when the Big Bang happened, it just like went straight through these black holes. And so they let's say the Big Bang wouldn't have pushed the black holes away like further out of our universe.
Yeah. So in his model that you basically a universe evolves once it's in existence, it evolves for trillions of years, perhaps. And the endpoint of all the matter in the universe is really surprising. That there's really no escape from the black holes that start to form because as I say, they're kind of irreducible. Once you have a black hole, there's no garbage can you can throw it into. You throw it into a garbage can, the black hole gets bigger. It swallows the mass of the garbage can. So in particular, yes, it's essentially a black hole. As I said, in its purest form, a black hole only has three properties. It only has its mass, and it has its what's called its spin, or if it's rotating or not, and it can have a charge. It can have a electrical charge associated with it. But that's it. So it's really a region of the curvature of space-time. If you envision space-time as sort of a trampoline, and the more massive an object is, say the sun, then it makes a deeper depression in space-time, and that allows then a smaller object like a golf ball to roll around in the depression, the indentation made by the black hole or the curvature of space. But if you imagine a black hole, turn up the mass of the sun from a bowling ball and make it like infinite. So it's basically now vertical walls of the trampoline. That's sort of what a black hole is. It's just a place of infinite curvature. And so it doesn't really have any other properties. And so can that go through the Big Bang itself? Well, the Big Bang is sort of a singularity in some concepts, but in Roger Penrose's not. It doesn't have a singularity. The universe just kind of transitions, gets more and more diluted, and then at greater and greater timescales, eventually the energy is sufficient to nucleate the expansion of another universe, but there's no mechanism to destroy the black holes that build up. So there's no dissipation mechanism for them. So they just live forever.
Now, someone like Roger Penrose, genius, Nobel Prize winner, one of the smartest physicists ever, almost in your category, where his knowledge and experience perhaps equals yours. But he seems very confident in his theories about this. How can you really be confident in a theory like that?
Well, you really can't.
We don't really know.
Yeah, science is an empirical, is an empirical endeavor, which means that you have to base your credibility or credulity or belief in something on evidence. So you have some idea, you have a guess, and that becomes a hypothesis, and then you try to assemble as much information to support it and see how well does it explain things that have not been explained in the past. Does it raise internal contradictions? Does it have features that are more powerful than a pre-existing idea? And you keep going through the list of different virtues of a model or an idea. And if it has enough virtues and passes enough confrontations with observation, then you might call it a theory. It's funny because people say, oh, it's just your theory, or like, oh, evolution, that's just a theory. But in physics, remember, there's no way to prove something in physics. I can't prove that the Earth is a perfect sphere. In fact, it's not a perfect sphere. It has some distortions to it, but I can make the case that it's more spherical than it is flat. And in doing so, I have to provide evidence for that claim. And then someone else can come along and say, actually, no, it's not perfectly spherical. It has these distortions, and it's actually slightly shaped like a pear, and it has these different properties. So only by doing that do we have, a closer and closer zeroing in on the quote truth. But we can't, very different from mathematics or, computer science or something. You can make a proof in mathematics which is not refutable unless, the laws of logic are wrong. And then in which case you're trying to use the laws of logic to prove that the laws of logic are not consistent.
It's interesting though, because math, everything derives from some first principles, right? So mathematics relies on the basic concepts of set theory.
Yes.
And from set theory, we can build a set of axioms that explains all of math. But if we weren't using set theory, and I don't know why we wouldn't, the rules would be different and we'd be proving different things. But set theory conveniently describes how we count, basically, and matches that perfectly.
That's right. Yeah.
So with physics, like, it seems like the first principles sometimes change. So we had, Aristotle, but then we had Isaac Newton, then we had Einstein, then we had quantum mechanics. And it's sort of like the height of creativity. Physics is very creative in the sense that there's proving things in physics and then we assume that they're true. But then there's another group of physicists that come along and say, you know what, I'm going to change the rules for a little while because we don't really know what the real first principles are.
Yeah, I wouldn't say that they're guided by a desire to change the rules. It's that either there's two different ways that scientific discoveries happen. One is that we discover something serendipitously. We look at Mercury and we say, wow, that's weird. Mercury is moving in this weird way. And it's not predicted or explainable using the theory of universal gravitation of Isaac Newton. So then somebody would say, I'm going to explain that effect, or retrodict, not predict it, but retrodict it. I'm going to say that
I didn't know there was a word for that.
Yeah, it's sort of, or post-diction instead of prediction. In other words, you knew that this was a problem, and even Newton knew it was a problem. They were quite astute even in the 1800s. But they didn't know the resolution of it because you can't predict it. You cannot explain, rather, why Mercury behaves in this strange way using Newtonian gravity alone. You need a new conception of gravity, which is what Einstein came along and did. And then there's another thing that can happen, which is that you can have a theory and then have a conclusion that comes from it that is then a prediction. So it actually happened with Newtonian gravity. There was a motion of the planet Uranus. By the way, did you know that NASA's commissioned me to change the name of the planet Uranus because it's so embarrassing that astronomers are, impossibly, tormented by the fact that saying Uranus has brought shame and embarrassment upon us. So
it's true. It was a horrible name.
So I've actually come up with a new name for it, and I'm prepared to reveal that on the James Altucher show right now.
What is the new name?
Erectum. So
okay, but wait. You know why it fails is
why?
Because all the planets except Earth are named after the Roman names of the Greek gods, right? So Mercury, Venus. Mercury is Hermes in Greek mythology. Venus is Aphrodite. Mars is Ares. Saturn is Saturn Cronus in Greek mythology. Jupiter is Zeus.
Yeah.
Neptune is Poseidon.
Yeah.
Uranus is Hephaestus, I believe. Pluto is Hades.
Yeah.
So, it's not a planet anymore, I guess. I don't know.
That's right. So when in sometime in the mid 1700s, people looked at the planet Uranus and its orbit, and they were looking at it, and they noticed, like, sometimes in the year it would be like a little too far to the left, and sometimes it was a little too far to the right. And they had great historical data for it. And just using Newton's laws of motion, universal gravitation, an astronomer named Leverrier, his name is Leverrier, a French astronomer, predicted that there would be another planet beyond the orbit of Uranus, and it would be pulling and slightly tugging on or delaying the orbit via its gravitational impact on Uranus. And he actually told somebody where to look, and they discovered it exactly where he predicted it, purely based upon the laws of Isaac Newton.
So how come they didn't apply that same idea to Mercury? Like, what happened with Mercury?
Oh, my dear friend, you're anticipating what I'm about to say next. So the same guy said, hey, this is great. And if you think about it, even though we can see Neptune, and they did discover it, it was kind of the first prediction of dark matter, right? In other words, they were saying there's some unseen matter that had a gravitational pull on something that we could see, visible light, in the form of the planet Uranus. And using this prediction, they were able to recover the position of the dark matter, which then you could see actually gives off some light. And that's the planet Neptune. So that was the discovery of Neptune. And so the same guy was a smart guy. So he said, well, this worked really well. Maybe there's another planet inside the orbit of Mercury, closer to the sun, that's doing the same thing. And the reason that we haven't seen it is because it's so close to the sun, it's blinded, and we're blinded to its presence. And so it was called Vulcan. So the planet Vulcan was predicted by the same guy using the same technique. And that's totally wrong. There is no planet closer to the sun than Mercury. But so in that case, dark matter hypothesis was wrong. And what was really needed was kind of like a version of string theory, or some new form of physics to augment the laws of Isaac Newton. And that was the laws of general relativity that we were talking about earlier. That was what Einstein came up with. So you had to actually change the relationship of the laws of physics, the underlying notion of space and time and their connectedness together, in order to have the correct explanation, retrodiction, for the orbit of Mercury. And that's in fact what happened.
So what is specifically the reason Mercury is a little off from Newtonian physics?
So there's an effect of near very strong gravitational massive objects like the sun that distorts space-time and causes slight indentations in a way that causes this advance of the orbit. Basically acts as a additional distortion, which then acts in distortion, meaning a curvature of space-time. All curvature of space-time is how we perceive the force of gravity. So there's an additional force of gravity due to the presence of the mass of the sun that's not accounted for. As you get closer and closer to the sun's surface, you actually pick up an extra term, an extra amount of gravity or curvature of space-time that is not present in Newtonian gravity, specifically because gravity affects time as well as space. So you had to basically add the effect of gravity on time in order to explain the effect of gravity and mass on objects, like massive objects like the planet Mercury. If it didn't have an effect on time, then you wouldn't have this advance, and therefore it was absent in Newton's laws.
I'm still not quite sure I fully understand gravity's effects on time, but that's okay. But the question I have is, was Einstein aware that his theories could be applied to Mercury before he came? Like, did he use Mercury as something he was thinking about before he came up with the theory of relativity? Like, did he curve fit to make it work?
No. He was definitely interested in this, and this was the first and really the only thing that he could think of that could provide a test bed at this time in 1914 for the observed behavior of his theory. So his theory made a prediction that prediction would explain Mercury's behavior. And then later it was realized there are many, many other consequences of Einstein's general relativity, including the fact that when there's an eclipse of the sun, as there is in April 8th of this year, which will be visible from Texas all the way up to like Illinois and Buffalo, New York and everything, and that a total solar eclipse provided an opportunity to view stars that were behind the sun and that were normally occluded by the brightness of the sun and rendered invisible. But during an eclipse, you can see stars and you can measure their positions. And there's an effect called gravitational lensing, where the gravity of the object, either a black hole or in this case the sun, bends the position of where the starlight should be, just like it bends the trajectory of how the planet Mercury moves. And so Einstein predicted that as well. And he actually made a math mistake, but eventually he corrected it. And then in 1919, so over 100 years ago, it was confirmed that there was, in fact, this distortion of starlight by the mass of the sun. And this was the great discovery that eventually did win him the Nobel Prize, even though people didn't want to admit it. It was just too astounding of a discovery to neglect. And so he didn't win the Nobel Prize in 1905 when he came up with relativity itself, or even in 1915 when he came up with the general theory of relativity that describes gravity. He only won it after this 1919 discovery in 1921. He won the 1921 Nobel Prize.
At Staples Business Advantage, nothing can top the smarts and instincts of the thousands of experts on our team. While AI excels at
processing data, automating tasks, and providing insights for better decision-making.
And when they're used together,
They are far more powerful than either is alone.
Whoa.
I've never felt more alive.
Let Staples Business Advantage use today's latest innovations, plus our team's experience, to make business easier for you.
Sign up today and save 20%.
Staples Business Advantage.
Business is
Human.
Stock have too high a price? Buy a slice. Trade fractional shares of your favorite U.S. stocks and ETFs in any dollar amount you choose with zero commissions online. Get started at Fidelity.com/stocks by the slice. Fractional share quantities can be entered to 3 decimal places if the value of the order is at least 1 cent. Dollar-based trades can be entered to 2 decimal places. Sell orders are subject to an activity assessment fee from 1 cent to 3 cents per $1,000 of principal. Fidelity Brokerage Services, LLC. Member NYSE, SIPC.
Now, how come his theories don't explain dark matter? Like, why is there dark matter? Why couldn't it be the case that what he's really predicting is that there's some supermassive black hole, unbelievably massive, that's further than our ability to see it? It went in the other direction when the Big Bang happened, whatever. And that could be the reason why we experience some weird gravitational tendencies.
Well, there are people that conjecture that dark matter is the manifestation of ordinary matter in another dimension. We don't have any evidence of that. Like it could be just as if you have, two different. Imagine you have two different infinite chessboards, right? And on the chessboards are living some creatures that only are two-dimensional. They live in this flatland, as it's called. And then there's another chessboard, and that chessboard is separated by, it could be 1 millimeter away. If they can't move into that third dimension, either set of creatures on either two-dimensional chessboard, they don't have any access to it using light. But if gravity could propagate from one chessboard to the other chessboard, then you could detect the presence of this other universe, this other flatland, merely by looking at the effects on objects in your own chessboard. So the pieces, or these flat two-dimensional chess pieces, would move around differently because they might be tugged upon by the gravity of another object in another universe that's actually a very short distance away. And that's these have been explored by people like Lisa Randall and other people. There's no evidence for this, but that is exactly what you're saying is one of the explanations of dark matter.
So this is why I think physics is, again, a super creative discipline, because you have these things that are quote unquote real, that are happening, but we don't really know why. And we have to just be as creative as possible, even crazy. Like there's other dimensions and the multiverse, and every theory is basically crazy about the universe. But in physics, you're allowed to be as crazy as possible. Sometimes even better to be, there's 12 dimensions and strings and all these things, and that's rewarded because good creativity backed somehow by a mathematical model that you might even make up to support your theory is rewarded in physics.
Yeah, no, there are but the issue is that it might just be kind of an example of science fiction, right? I mean, there's more things you can theorize than you can actually expect to exist in reality. So
well, and I have a question about that. I'm sorry to keep interrupting, but I get curious. So, like, the concept of a wormhole, is that science fiction? Is it theoretical, or is it actual? And if it's actual, is it likely to be actual, or is it actually actual?
No, I mean, there's absolutely no evidence for wormholes. There is abundant evidence for black holes. Wormholes are sort of an interesting, almost cultural phenomenon more than they are a practical physics, instance of something that could truly be measured or important in science. So there's no necessity for wormholes. But there is sort of a necessity for black holes because you have these objects of the endpoints of which are gravitationally collapsed objects, and there's no way to escape. Once you start gravitational collapse of a massive star, as you suggested early on, it's basically a runaway positive feedback loop. There's no way to avoid collapsing to a singularity where there's absolutely infinite curvature. Now, you can't see the singularity because it's obscured by this event horizon, or if you like, any signature of it would be contained within the event horizon, and you cannot penetrate the event horizon. There's no escape velocity that allows you to get a signal out from inside the event horizon to any distance away from it.
So like radio waves, light waves,
Nope.
every type of energy or frequency, the gravity is too strong for it.
So the event horizon is the fictitious surface within which the escape velocity of any object, a baseball, a photon, a neutron, a crouton, is the speed of light. And then it only gets larger and larger as you get closer and closer to the singularity itself. So at the singularity, the escape velocity is infinite. And so it's impossible to generate anything that goes faster than the speed of light made of matter or energy. But, all the more so is it impossible, to a much greater degree to do something that's infinite velocity. That would be the escape velocity at the singularity itself.
So I forget if this is an Einstein thing, but if an object goes the speed of light, doesn't it get like infinitely massive, or what's the properties of so inside a black hole, doesn't it just like, is it infinitely massive there, even though it's a singularity?
So mass is the property that we associate with difficulty in moving something. So it's sort of like inertia. Mass is how much force do you have to apply to something to get it to travel with some acceleration. So if you have a mass, if you want to move something and you want it to have an extremely high acceleration, say start from zero and accelerate to the speed of light, then that you're taking some finite force and you're dividing by a very large number. The acceleration in F equals ma would be extremely large. So the mass would then be equal to zero. So the only way to get something to move, infinite speed or, faster than the speed of light would be if it had less than zero mass. So all photons, all particles of light in the vacuum, they travel at the speed of light. And then any massive object to get to a given velocity, the equation that tells you how much energy you have to provide looks like 1 divided by the square root of 1 minus the velocity over the speed of light squared. So let's say you want to go at the, half the speed of light. So the energy you're going to have to provide that object is going to be many, many times its so-called rest mass. So you're going to have to supply energy more than all the matter energy that it has itself. And that E equals mc squared equation is the equation that gives, the power of a nuclear weapon. In other words, the square of the speed of light is a tremendous number. And so, so any finite amount of mass will require an infinite amount of energy to travel at the speed of light. And anything that's almost zero mass or is zero mass, like a photon, can travel only at the speed of light. There's no way to slow down a photon in the vacuum.
Why is the speed of light a limit? Like, is it like an arbitrary limit that happened to be just like magically the number and nothing can go faster than this?
Well, so what ended up happening was in the 1850s, in the middle of the 1800s, James Clerk Maxwell, is a Scottish physicist. He was looking at the laws of electricity and magnetism and came up with these 4 equations called the Maxwell equations. And these are for what are called differential equations. And they describe how big an electric field does a charge produce, how big a magnetic field does a current produce. And then it was found that you could take these 4 equations and combine them in a certain way. And you got 2 equations for the propagation of waves, so that you'd have a field, an electromagnetic field, either a magnetic field or an electric field. And then it would oscillate sinusoidally with a given frequency in time and a given period or wavelength in space. So, and it was found that when he calculated what that speed is of a wave, which is a pretty straightforward thing to do in physics, the speed that emerged was a speed that was very, very close to the speed of light, as it was known at that time. It was the speed of light. It was very difficult to measure, but it was known it was greater than about 200,000 kilometers per second and less than 400,000. It's exactly 300,000 kilometers per second. But back then, so it was very suspiciously close. And so he realized that actually these waves would then be propagating with a speed of the speed of light, as it was known at that time. But the problem was they didn't know about any waves that could propagate without there being some kind of medium, like an ocean or air in a room for a sound wave. They didn't know of any waves that could propagate without some kind of substance to support them. And so he conjectured this substance called the ether, that there must be some, basically this invisible fluid that fills all of the universe called the ether. And then for about 50 years, people tried to see if they could detect the ether, and they couldn't find that they found they couldn't detect the ether. And in fact, there was no way to even predict, a value that would be consistent with what these measurements seem to indicate. So eventually we got rid of the ether, and then it was a big puzzle how you could have, light traveling always at the speed of light without any substance supporting it. And that's where Einstein comes in 1905, 50 years later or so, and comes up with the notion that light only travels at the speed of light. And light is an electromagnetic wave. And no matter what reference frame you're in, no matter how fast you're moving, if you turn on a flashlight, that flashlight will always travel at the speed of light, as observed by any observer in any of the reference frames. Even if you're traveling at half the speed of light, if that was even possible, and you turn on a flashlight, you will still see the light traveling away from you at the speed of light. And so it became really the only way to have that happen was to say that when something is in motion, either the time for that observer slows down, or the length as observed by those observers gets smaller. So either time gets longer or distances get shorter, or both. And these effects were then measured in the laboratory. So you could actually measure things at very high speeds and measure how long they live for, if it was a particle. And if it was moving very close to the speed of light or, some very fast velocity, it would actually live longer than it would and decay at a later time than its brother in a jar sitting out stationary at rest on the Earth's surface. And these were all measured.
So how did he figure out, though, that light didn't need anything to propagate through? It didn't need an ether.
So Einstein, so that was observed experimentally that there was no detectable ether. And so the explanation for it is really relies on the generation of how electromagnetic waves are generated. So if you have a magnet and you have a wire, if you move that magnet inside the wire, it will generate an alternating electric current. The current will oscillate back and forth inside the wire. And that oscillation shows you there's a connection between current is just the motion of electric charges, and a magnetic field is a collection of, is a collective property of matter that generates this magnetic field. And so as long as you have a magnetic field and it's moving, there's something moving in it, it will generate a changing electric current. And once you have a changing electric current, that generates a magnetic field. So if you have a current in a wire, it will generate a magnetic field, a constant magnetic field. And if you alternate the current of the wire, it will generate an alternating current. And then if you do both of those at the same time, moving a magnet and having an oscillating current, you can actually generate a self-sustaining electromagnetic wave. So it's sort of hard to visualize. It's like the vacuum has the potential at all points in time and then in space to have a light wave or an electromagnetic field. And then in certain places, we call an excess of probability to find an electromagnetic field a charge or a magnetic field. So it's really kind of a self-propagating thing. It's almost like a wave that generates itself. There's nothing waving. There's no medium. Like the vacuum is changing in the sense that it has a higher or lower chance of having this value for an electric or magnetic field. And we have observed that, and that's what's called quantum field theory. We've observed a quantum version of it. We have a classical version. Maxwell's a classical field theory, and quantum electrodynamics, Richard Feynman, that's a quantum field. And we have a very good description of all the forces of nature except for gravity, both classically and quantum mechanically. But gravity, we don't have a quantum mechanical description of. So we don't know actually if there's a quantum analog of a photon. People call it the graviton, but we actually have never observed it.
And even though gravity has many of the properties of light and other electromagnetic waves.
That's right. Yeah. So gravity, there's a funny meme where you look at, it's like a picture of this guy Coulomb who discovered the equivalent law of universal gravitation, but for electric fields. And then he's like looking over the shoulder on an exam of Isaac Newton, who wrote down the law of, inverse square law. And so, yeah, exactly. Both laws are inverse square laws, and both laws have properties of wave-like solutions. So there's gravitational waves, there's electromagnetic waves, there's static, but there are big differences between gravity and electricity and magnetism too. The biggest one being that you have only attractive force of gravity. But you can have negative or positive, attractive or repulsive electromagnetism. There's no anti-gravity. There's no negative gravitational charges, for example.
So, and this is the theory that maybe gravity might be coming from a nearby universe. So it looks like things in our universe, but we don't quite understand it because it's ultimately some property of another universe.
Right. Yeah, that's right. So we're not sure about that. I mean, part of what my research is and looking for the earliest signals from the Big Bang's origin, so-called inflation, would be to potentially discover physical evidence for the origin of gravity, in the sense that, if inflation took place, there will be a quantum version of gravity called a graviton, and those gravitons will be produced in a way that we could detect them using the polarization properties of the cosmic microwave background. That's what I study, as we talked about several times. So, kind of what we're doing is looking for primordial waves of gravity in the early universe that would be basically the oldest fossil thing you could see at all. So not 400 million years like this black hole in this galaxy, if that's what it turns out to be, and not 400,000 years like the cosmic microwave background, but actually something that's, 4 trillionths of a trillionth of a trillionth of a second after the Big Bang, like we talked about at my TED Talk here in San Diego, which was unbelievably almost 10 years ago this year. James, can you believe it?
2014. That's when we were on the same stage.
That's when we met. That's when we met in the green room.
I feel like I must be going... there must be greater gravitational pull on me because I feel like time's going faster, or less gravitational pull on me.
Yeah.
Time's going faster right now. That was the physics conversation. Fascinating stuff as always. And now we talk about more life, personal stuff in another episode. And it got kind of reflective for me. So stay tuned for the next version of Brian Keating.
At Staples Business Advantage, our experts can help you find furniture that fits any design and budget, while AI can
Recommend products based on preferences, generate 3D models for visualization, and optimize space planning for office furniture.
take advantage of our team's eye for style and design.
And my eye for, wait, I have no eyes. Only algorithms.
At Staples Business Advantage, furnishing your office is easy. And with the best warranty in the business, we're committed to you now and down the road.
Sign up today and save 20%.
Staples Business Advantage.
Business is
Human.
Building a portfolio with Fidelity Basket Portfolios is kind of like making a sandwich. It's as simple as picking your stocks and ETFs, sort of like your meats and other topics, and managing it as one big, juicy investment. Now that's pretty good. Learn more at fidelity.com/baskets. Investing involves risk, including risk of loss. Fidelity Brokerage Services, LLC. Member NYSE SIPC.